Hello and welcome to this video walkthrough on analyzing stock market data using Python. In this Jupyter notebook, we will be focusing on technology stocks such as Apple, Amazon, Google, and Microsoft. We will be using the finance library to retrieve stock information and visualizing the data using Seaborn and Matplotlib. Our analysis will include calculating moving averages, daily returns, and correlations between different stocks. Additionally, we will be using the long short-term memory (LSTM) method to predict future stock prices. So, let's dive in and see how we can use Python to analyze and predict stock market trends. Hello and welcome to this video walkthrough on analyzing stock market data using Python. In this Jupyter notebook, we will be focusing on technology stocks such as Apple, Amazon, Google, and Microsoft. In the current cell, we are introduced to the concept of time series data, which is a series of data points indexed in time order. We will be using this type of data to analyze the stock market. We will be using the finance library to retrieve stock information and visualizing the data using Seaborn and Matplotlib. In this notebook, we will be looking at a few ways of analyzing the risk of a stock based on its previous performance history. We will also be predicting future stock prices through a long short-term memory (LSTM) method. The current cell also lists the questions we will be answering along the way, such as the change in price of the stock over time, the daily return of the stock on average, the moving average of the various stocks, the correlation between different stocks, and how much value we put at risk by investing in a particular stock. We will also attempt to predict future stock behavior using LSTM. In the next cell, we will be getting the data and loading it to memory using the finance library. To do this, we will be installing the finance library using the pip install command. But we will discuss that in the next cell. So, let's move on to the next cell and get started with retrieving the stock data. In this cell, we are installing the finance library using the pip install command. This library will allow us to retrieve stock information for our analysis. The Q flag is used to suppress any output during the installation process. We will be using this library in the next cell to retrieve the stock data. Hello and welcome back. In this cell, we are importing the necessary libraries for our analysis. We are using Pandas and NumPy for data manipulation, Matplotlib and Seaborn for data visualization, and Finance for retrieving stock information from Yahoo Finance. We are also setting up the list of technology stocks we will be analyzing, which includes Apple, Google, Microsoft, and Amazon. Next, we are setting the start and end dates for our data grab using the datetime library. We will be retrieving data for the past year. Then, we are using a for loop to retrieve the stock data for each company in our tech list using the if.download function from the finance library. We are storing each company's data in a variable with its name as the variable name. After that, we are creating a list of the company data and concatenating them into a single data frame using the concat function from Pandas. We are also adding a column to the data frame for each company's name. Finally, we are displaying the last 10 rows of the data frame using the tail function from Pandas. That's it for this cell. In the next cell, we will be reviewing the content of our data and performing some basic data analysis. In this cell, we are reviewing the content of our data and checking its basic properties. We can see that the data is numeric and the date is the index of the data. However, we also notice that weekends are missing from the records. We then use the .describe function to generate descriptive statistics about our data. This function summarizes the central tendency, dispersion, and shape of a dataset's distribution, excluding NaN values. It can analyze both numeric and object series, as well as data frame column sets of mixed data types. In the next cell, we will use this function to generate summary statistics specifically for the Apple stock data. In this cell, we are using the .describe function to generate summary statistics for the Apple stock data. This function provides us with information about the central tendency, dispersion, and shape of the dataset's distribution. We can see that the data includes the opening, high, low, and closing prices, as well as the adjusted closing price and volume. We can also see the count, mean, standard deviation, minimum, maximum, and quartile values for each column. In the next cell, we will review the content of our data further and use the .info method to print information about the data frame, including the index D type, columns, non-null values, and memory usage. Welcome back. In the current cell, we are reviewing some basic properties of our data. We notice that weekends are missing from the records, which means we only have 255 records for 1 year. Next, we will use the .info method to print information about our data frame. This method provides us with information about the index D type, columns, non-null values, and memory usage. In the next cell, we will use this method specifically for the Apple stock data. Stay tuned. In this cell, we are specifically looking at the Apple stock data. We use the .info method to print some general information about the data frame, including the index D type, columns, non-null values, and memory usage. We can see that we have 251 entries, which means we have data for 251 trading days in the past year. We also have 7 columns, including the opening, high, low, and closing prices, as well as the adjusted closing price and volume. In the next cell, we will focus on the closing price specifically and learn more about its importance in tracking a stock's performance over time. In this cell, we are discussing the importance of the closing price in tracking a stock's performance over time. The closing price is the last price at which the stock is traded during the regular trading day, and it is the standard benchmark used by investors to track a stock's performance. In the next cell, we will see a historical view of the closing price for our list of technology stocks, which includes Apple, Amazon, Google, and Microsoft. We will use the matplotlib library to create a plot that shows the closing price for each stock over time. But before that, let's move to the next cell to learn more about the Apple stock data specifically. In this cell, we are creating a historical view of the closing price for our list of technology stocks. We start by creating a figure with a size of 15 by 10 using the plt.figure method. We then adjust the subplots using the plt.subplots_adjust method to make sure they fit nicely in the figure. Next, we use a for loop to iterate through our list of companies and plot the adjusted closing price for each company using the company adjective close plot method. We also set the y-axis label to adjective close, remove the x-axis label using plt.label none, and set the title of each subplot to closing price of company name. Finally, we use the plt.tight_layout method to make sure the subplots are nicely spaced out. This cell outputs a figure with 4 subplots, each showing the historical view of the closing price for one of our technology stocks. In the next cell, we will learn about the importance of trading volume in technical trading. In this cell, we are discussing the concept of trading volume in the stock market. Trading volume refers to the amount of shares of a security that are traded between its daily open and close. It is an important input for technical traders, as changes in trading volume over time can indicate changes in market sentiment. In the next cell, we will plot the total volume of stock being traded each day for our list of technology stocks. In this cell, we are creating a historical view of the total volume of stock being traded each day for our list of technology stocks. We start by creating a figure with a size of 15 by 10 using the plt.figure method. We then adjust the subplots using the plt.subplots_adjust method to make sure they fit nicely in the figure. Next, we use a for loop to iterate through our list of companies and plot the volume traded each day for each company using the company volume plot method. We also set the y-axis label to volume, remove the x-axis label using plt.label none, and set the title of each subplot to sales volume for company name. Finally, we use the plt.tight_layout method to make sure the subplots are nicely spaced out. This cell outputs a figure with 4 subplots, each showing the historical view of the total volume of stock being traded each day for one of our technology stocks. In the next cell, we will learn about calculating the moving average for the stock. In this cell, we will be calculating the moving average for the stock. The moving average is a technical analysis tool that smooths out price data by creating a constantly updated average price over a specific period of time. This can be 10 days, 20 minutes, 30 weeks, or any time period the trader chooses. In the next cell, we will see the code for calculating the moving average for our list of technology stocks and plot the results. In this cell, we are calculating the moving average for our list of technology stocks. The moving average is a technical analysis tool that smooths out price data by creating a constantly updated average price over a specific period of time. In this case, we are using 10, 20, and 50 days as our time periods. We use a for loop to iterate through each time period in each company in our list. We then create a new column for each company that calculates the moving average for the specified time period using the rolling method. Finally, we plot the adjusted closing price and the moving averages for each company using subplots. We can see that the best values to measure the moving average are 10 and 20 days because we still capture trends in the data without noise. In the next cell, we will analyze the risk of the stock by calculating the daily returns for the Apple stock. In this cell, we continue our analysis of the Apple stock data by looking at its daily returns. We want to analyze the risk of the stock, so we need to take a closer look at the daily changes of the stock, and not just its absolute value. We use pandas to retrieve the daily returns for the Apple stock by using the pct_change method on the adjusted close column. In the next cell, we will plot the daily return percentage for all the technology stocks in our list, including Apple, Google, Microsoft, and Amazon. We'll use the subplots method from Matplotlib to create a 2x2 grid of subplots, one for each company, and plot the daily return percentage for each company on its respective subplot. In this cell, we're calculating the daily return percentage for each company in our list. We're using the pct_change function to find the percent change for each day. Then, we're plotting the daily return percentage for each company using subplots. We're creating a 2x2 grid of plots, with each plot showing the daily return percentage for one of the companies in our list. We're using different markers and line styles to make the plots more visually appealing. Finally, we're using tight_layout to make sure the plots are properly spaced out. In the next cell, we'll create a histogram and CAD plot to get an overall look at the average daily return. In this cell, we're going to create a histogram and CAD plot to get an overall look at the average daily return. We'll be using Seaborn to create both plots on the same figure. A histogram is a graph that shows the frequency distribution of a set of continuous data. It's a way to visualize how often certain values occur within a range. A CAD plot, on the other hand, is a way to estimate the probability density function of a continuous random variable. It's a smooth curve that shows the distribution of the data. We'll be creating a 2x2 grid of plots, with each plot showing the daily return percentage for one of the companies in our list. We'll be using different markers and line styles to make the plots more visually appealing. Finally, we'll be using tight_layout to make sure the plots are properly spaced out. But that's all for the next cell. In this cell, we're just setting up the idea of creating a histogram and CAD plot to get an overall look at the average daily return. In this cell, we are creating a figure with 4 subplots, one for each company in our list. We are using a for loop to iterate through each company and plot a histogram of their daily returns. The x-axis represents the daily return percentage and the y-axis represents the count of how many times that percentage occurred. We are also adding labels and titles to each subplot to make it easier to understand which company we are looking at. This is a great way to visualize the daily returns of each company and compare them to each other. In the next cell, we will be looking at the correlation between the closing prices of different stocks. In this cell, we are discussing the concept of correlation between different stocks' closing prices. Correlation is a statistic that measures the degree to which two variables move in relation to each other, and it has a value that must fall between -1.0 and +1.0. However, correlation only measures association and doesn't show if one variable causes the other or if the association is caused by a third factor. Next, we are going to analyze the returns of all the stocks in our list. To do this, we will build a data frame with all the close columns for each of the stock's data frames. This will allow us to make a new data frame called tech_RETS that will contain the percentage change in the closing prices of each stock. We will be looking at this in the next cell. In this cell, we are grabbing all the closing prices for the technology stock list and putting them into one data frame called closing_DF. We are using the pandas.reader library to retrieve the data from Yahoo Finance. Next, we are creating a new data frame called tech_RETS by using the PCT_change method on the closing_DF data frame. This method calculates the percentage change between the current and a prior element. We are using this method to calculate the daily returns for each stock in the list. The output of this cell shows the first 5 rows of the tech_RETS data frame, which contains the daily return percentage for each stock in the list. The first row is all NaN values because there is no prior element to calculate the percentage change from. In the next cell, we will be comparing the daily percentage return of two stocks to check how correlated they are. But first, we will compare a stock to itself to see how it looks. In this cell, we will be comparing the daily percentage return of two stocks to see how correlated they are. To start, we will compare a stock to itself. In the next cell, we will compare the daily percentage return of two different stocks. In this cell, we are comparing the daily percentage return of Google to itself. The purpose of this is to see if there is a linear relationship between the two. We are using the SNS.jointPlot function to create a scatter plot with Google on both the X and Y axes. The plot shows the relationship between the daily returns of Google to itself. If the plot shows a straight line, it means that there is a perfect linear relationship between the two. In the next cell, we will compare the daily percentage return of two different stocks to see if there is a correlation between them. In this cell, we are comparing the daily returns of Google and Microsoft to see if there is a correlation between them. We are using the SNS.jointPlot function to create a scatter plot with Google on the x-axis and MSFT on the y-axis. The plot shows the relationship between the daily returns of Google and Microsoft. If the plot shows a straight line, it means that there is a perfect linear relationship between the two. In the next cell, we will compare the daily percentage return of two different stocks to see if there is a correlation between them. In this cell, we're going to talk about how to compare the daily returns of different stocks to see if there is a correlation between them. If two stocks are perfectly and positively correlated, we should see a linear relationship between their daily return values. To make this comparison analysis easier, we can use Seaborn and Pandas. We can use the SNS.pairPlot function to automatically create a scatter plot for every possible combination of stocks in our technology stock ticker list. In the next cell, we'll see an example of how to use this function to create a visual analysis of all the comparisons. In this cell, we're going to compare the daily returns of different technology stocks to see if there is a correlation between them. We can use Seaborn and Pandas to make this comparison analysis easier. To do this, we can simply call the SNS.pairPlot function on our data frame, which will automatically create a scatter plot for every possible combination of stocks in our technology stock ticker list. In this case, we're using the tech_RETS data frame. By looking at the scatter plots, we can see if there is a linear relationship between the daily return values of two stocks. If two stocks are perfectly and positively correlated, we should see a linear relationship between their daily return values. In the next cell, we'll see an example of how to use this function to create a visual analysis of all the comparisons. In this cell, we are looking at the daily returns of all the technology stocks in our list. We can see a correlation between Google and Amazon daily returns, which we might want to investigate further. We have been using the SNS.pairPlot function to create scatter plots of the daily returns, but now we will use SNS.pairGrid for more control over the figure. This will allow us to specify what kind of plots go in the diagonal, upper triangle, and lower triangle of the figure. In the next cell, we will set up our figure by calling SNS.pairGrid on the tech_rets data frame and dropping any missing values. We will then use map_upper to specify what the upper triangle will look like, map_lower to define the lower triangle, and map_diag to create a series of histogram plots of the daily return. Stay tuned for the next cell to see how this is done. In this cell, we are setting up a figure to plot the daily returns of all the technology stocks in our list. We are using the SNS.pairGrid function to create a grid of subplots, where each subplot will show the relationship between two different stocks. First, we name our figure return_fig and call SNS.pairGrid on the tech_rets data frame, dropping any missing values. Next, we use map_upper to specify what the upper triangle of the figure will look like. In this case, we are using a scatter plot with the color set to purple. We can also define the lower triangle of the figure using map_lower. Here, we are using a kernel density estimate plot, KD plot, with a cool color map, blue-purple. Finally, we defined the diagonal of the figure using map_diag. We are creating a series of histogram plots of the daily return with 30 bins. In the next cell, we will use this figure to investigate the correlation between different technology stocks. Stay tuned. In this cell, we are setting up a figure to plot the daily returns of all the technology stocks in our list. We use SNS.pairGrid to create the figure and then use map_upper to specify a scatter plot with a purple color for the upper triangle. We also define the lower triangle in the figure using map_lower, which creates a KD plot with a cool color map. Finally, we use map_diag to create a series of histogram plots of the daily return. This figure will help us investigate the correlation between different technology stocks. In this cell, we are discussing the possibility of creating a correlation plot to get numerical values for the correlation between the daily return values of different technology stocks. This plot will help us investigate the relationship between different stocks. We also mentioned that by comparing the closing prices, we have already seen an interesting relationship between Microsoft and Apple. In the next cell, we will create a figure with two subplots using the SNS.heatmap function to visualize the correlation of stock return and the correlation of stock closing price. But for now, let's focus on the idea of a correlation plot and how it can help us understand the relationship between different stocks. In this cell, we are creating a figure with two subplots to visualize the correlation between different stocks. The first subplot shows the correlation of stock return using a heat map with annotations, while the second subplot shows the correlation of stock closing price using a similar heat map. This figure will help us investigate the relationship between different technology stocks. In the next cell, we will see the numerical and visual correlation between Microsoft and Amazon, which we suspected from our previous pair plot. We will also discuss how to quantify risk by comparing the expected return with the standard deviation of the daily returns. In this cell, we see that Microsoft and Amazon have the strongest correlation of daily stock return, which confirms what we suspected from our previous pair plot. It's also interesting to note that all the technology companies are positively correlated. Moving on, we will now discuss how to quantify risk when investing in a particular stock. One basic way to do this is by comparing the expected return with the standard deviation of the daily returns. We will explore this further in the next cell. In this cell, we are looking at how to quantify risk when investing in a particular stock. We start by dropping any missing values from the tech_rets data frame and assigning it to a new variable called rets. Next, we create a scatter plot to visualize the relationship between the expected return and the risk of each stock. The size of each point on the plot represents the area of the circle, which is calculated using the formula np.pi20. We then label each point on the plot with the name of the corresponding stock using the plt.annotate function. The x-coordinate of each point represents the expected return, while the y-coordinate represents the risk. By looking at this plot, we can see that all the technology companies have a positive correlation between expected return and risk. Additionally, we can see that Microsoft and Amazon have the strongest correlation of daily stock return, which confirms what we suspected from our previous pair plot. In the next cell, we will focus on predicting the closing price stock price of Apple Incorporated. In this cell, we are going to focus on predicting the closing price of Apple's stock. We start by creating a markdown cell with a title that explains what we are going to do. In the next code cell, we will use the pandas.reader library to retrieve the stock information for Apple. We will use the get_data_Yahoo function to get the stock information for Apple from January 1, 2012 to the current date. We will assign this data to a variable called df. We will then display this data using the df variable. This will give us an idea of what the data looks like and what we will be working with in the next steps. In this cell, we are retrieving stock information for Apple using the pandas.reader library. We are using the get_data_Yahoo function to get the stock information for Apple from January 1, 2012 to the current date, and assigning it to a variable called df. We then display this data using the df variable, which shows us the opening price, closing price, high and low prices, volume of stock being traded, and more for each day. In the next cell, we will use this data to create a plot of the closing price history for Apple's stock. In this cell, we are creating a figure to visualize the closing price history for Apple's stock. We start by setting the size of the figure to 16 by 6 using plt.figureFigSize equals 16,6. We then set the title of the plot to close price history using plt.titleClosePriceHistory. Next, we plot the closing price data for Apple stock using plt.plotDFClose. The x-axis of the plot represents the date, while the y-axis represents the closing price in US dollars. We label the x-axis as date and the y-axis as close price USD, dollar, using plt.labelDate, font size equals 18, and plt.labelClosePriceUSD, dollar, font size equals 18, respectively. Finally, we display the plot using plt.show. In the next cell, we will create a new data frame with only the close column, convert it to a NumPy array, and get the number of rows to train the model on. In this cell, we are creating a new data frame called data that only contains the close column from the df data frame. We then convert this data frame to a NumPy array called dataset. Finally, we calculate the number of rows to train the model on by taking 95% of the length of the dataset array and rounding up using the np.ceil function. The output of this cell is the value of training_data_len, which tells us the number of rows we will use to train our model. In the next cell, we will scale the data using the min-max scaler function from the Exploratory library. In this cell, we are scaling the data using the min-max scaler function from the Exploratory library. We create an instance of the min-max scaler class and set the feature range to be between 0 and 1. We then apply the fit_transform method to the dataset array to scale the data. The output of this cell is the scaled_data array, which contains the scaled values of the closing price data for Apple stock. Scaling the data is an important step in preparing it for use in our model, as it ensures that all the values are within the same range and prevents any one feature from dominating the others. In this cell, we are creating the training data set for our LSTM model. We start by creating a scaled training data set from the scaled_data array, which we previously created in the last cell. We then split the data into x_train and y_train data sets. To do this, we use a for loop to iterate through the train_data array, starting at index 60. For each iteration, we append the previous 60 values of the train_data array to the x_train array, and the current value of the train_data array to the y_train array. We then print out the x_train and y_train arrays for the first two iterations to see what they look like. After creating the x_train and y_train arrays, we convert them to NumPy arrays using the np.array function. We then reshape the x_train array to have a shape of x_train.shape0, x_train.shape1, 1, using the np.reshape function. This is necessary because the LSTM model expects a three-dimensional input with the shape batch_size, time steps, input_dim. Overall, this cell is preparing the data for use in our LSTM model by creating the training data set and reshaping it to the correct format. In this cell, we are building an LSTM model using the Keras library. The model has two LSTM layers with 128 and 64 units respectively, followed by two dense layers with 25 and 1 units respectively. We then compile the model using the Atom Optimizer and mean squared error loss function. Finally, we train the model using the fit method with x_train and y_train datasets, a batch size of 1 and 1 epoch. The output shows the loss value after training. In the next cell, we will create a testing dataset and use the train model to make predictions. In this cell, we are creating a testing dataset for our LSTM model. We start by creating a new array called test_data that contains the scaled values from index 1543 to 2002. We then create the x_test and y_test datasets using a for loop. The x_test dataset is created by appending 60 values from test_data to the array for each iteration of the loop. We then convert x_test to a NumPy array and reshape it to have a shape of x_test.shape0, x_test.shape1, 1, to fit the LSTM model's input format. Next, we use the train model to make predictions on the x_test dataset and store the predicted values in the predictions array. We then use the scalar.inverse_transform method to convert the predicted values back to their original scale. Finally, we calculate the root mean squared error, RMSE, between the predicted values and the actual y_test values. The output of this cell is the RMSE value. In the next cell, we will plot the data to visualize the model's performance. In this cell, we are visualizing the performance of our LSTM model by plotting the training and validation data, as well as the predicted values. We start by creating two data frames, train and valid, which contain the training and validation data respectively. We then add a new column to the valid data frame called predictions, which contains the predicted values generated by our model. Next, we use the PLT library to create a plot of the data. The plot has a title of model, with the x-axis labeled as date and the y-axis labeled as close price USD, $. We plot the close values from the train data frame using plt.plotTrainClose, which creates a blue line on the plot. We then plot the close and predictions values from the valid data frame using plt.plotValidClose, predictions, which creates an orange line for the actual close values and a green line for the predicted predictions values. Finally, we add a legend to the plot using plt.legendTrain, val, predictions, log equals slower right, which labels the blue line as train, the orange line as val, and the green line as predictions. The log equals slower right argument specifies the location of the legend on the plot. The output of this cell is the plot of the data, which shows the actual close values in orange, the predicted predictions values in green, and the close values from the training data in blue. In the next cell, we will display the valid data frame to see the actual and predicted values. In this cell, we have the output of the valid and predicted prices. The valid variable contains the actual stock prices, while the predictions column contains the predicted prices generated by our LSTM model. The output is a table with the date, actual stock price, and predicted stock price for each day in the validation set. This information will be used in the next cell to visualize the performance of our LSTM model. But for now, let's focus on understanding the output of this cell. The table shows us how well our model is performing in predicting the stock prices. We can see that the predicted prices are close to the actual prices, but there are some differences. In the next cell, we will use this information to plot the actual and predicted prices and see how well our model is performing overall. In this cell, we have a summary of what we have learned so far in this notebook. We learned how to load stock market data from the Yahoo Finance website using uFinance, explore and visualize time series data using Pandas, Matplotlib, and Seaborn, measure the correlation between stocks, and measure the risk of investing in a particular stock. This summary serves as a reminder of what we have accomplished and what we can do with the stock data. If you have any questions, feel free to ask them in the comments below. In the next cell, we will continue with our analysis by using the LSTM model we created earlier to make predictions on the stock prices. In this cell, we don't have any code to look at. Instead, we have a summary of what we have learned so far in this notebook. We learned how to load stock market data from the Yahoo Finance website using uFinance, explore and visualize time series data using Pandas, Matplotlib, and Seaborn, measure the correlation between stocks, and measure the risk of investing in a particular stock. This summary serves as a reminder of what we have accomplished and what we can do with the stock data. If you have any questions, feel free to ask them in the comments below. In the next cell, we will continue with our analysis by using the LSTM model we created earlier to make predictions on the stock prices. In conclusion, we have successfully created and trained an LSTM model using Keras library and evaluated its performance on a testing data set. We have also visualized the model's performance and generated a table with actual and predicted stock prices. This is just the beginning of our analysis, and we will continue to use this LSTM model to make predictions on stock prices. Thank you for watching this video walkthrough, and I hope you found it informative and engaging.